popular performances have a warm-up act. I am going to be the warm-up act for a quite phenomenal presentation, which you will get in a minute or two. And my warm-up act is to tell you something about graduate facilities and education here at Balliol. And I think I've been chosen to do that largely because I go back to the very beginning of Holywell Manor as a graduate centre, which was founded as that in 1967. I will just be very quick about the key facts. It was the first graduate centre to be established by a traditional Oxford college. I think it's been copied in one form or another by all the other 30-odd colleges, none of which has succeeded in reproducing it in quite the same way. There's something in the Balliol, well, I was going to say DNA, but those of you who are at my morning lecture will know that I won't say that. But there's something in the Balliol spirit that seems to give rise to these occasional reachings out to new development. It was also the first mixed college residence because, as those of you will know well, in those days Balliol and all other colleges were single-sex. What we did was also quite remarkable, reaching out to St Anne's, then a women's college, and in fact the centre was formed as a joint residence between St Anne's and Balliol. Running through to the present day, it has a highly active middle common room. Those of you who may have been present at the 750th anniversary celebrations just 3 years ago will know that in addition to the main celebrations here in the college, the graduates put on a 750th anniversary festival, which was quite extraordinary. Simultaneous talks, a bit like today, in various locations, and a great party. They've done the same kind of thing more recently too. I like to think, I was Prefectus there for nearly 20 years, and I like to think that I in some ways initiated that spirit, because those were the days of what I call the Balliol Revolution, 68 to 75 roughly speaking. Christopher Hitchens, Martin Kettle, John Moynihan, the list goes on. Most of them, of course, have turned vastly to the right since they left Balliol. I don't know why we did that, but there we are. That's they would be able to tell you that side of it. I was actually asked to go in to the Graduate Centre as Prefectus, largely to do something about the revolution. And what I told the graduates when I arrived there as Prefectus in 1971 was to say, well, you've won. You now run the show. And they have. And they've run it magnificently ever since. I think that Balliol still leads the way in both graduate education and in graduate facilities. If you want to know more on the history of the centre, there's a production by Voices from Oxford. If you go from the Voices from Oxford website and simply type in Ghosts of Holywell Manor, you'll be able to get a potted version of the history of the manor. And there's only one other thing I want to say, which is that, as some of you will know from the literature that's been circulated, it is now possible under funding to Balliol to earmark funding for the Graduate Centre and for graduate facilities. But now I turn to the real show this afternoon, because you will now have the privilege of hearing how the Balliol graduate community has contributed to the work of a major international player. That's David Wark. David is a Fellow of the Royal Society. He's been a Fellow of Balliol in two capacities, first as a tutorial Fellow, now as a supernumerary Fellow, special supernumerary Fellow. I never know what all of these words mean, David, but there we are. He's very special, that's all I know, as you'll see in a moment. And of course, as Professor of Physics. He was actually born and educated in the United States, went to Caltech, which is where he did his PhD, was for a period at the Los Alamos National Laboratory as a postdoc, and he moved to the UK, I think, in 1990. He's spent his working life in an area of particle physics that deals with a particle that most of us don't even claim to begin to understand. There are trillions of them going through my body now, this very moment. They're called neutrinos. And he's going to tell us about that because in the lead up to the work that he's going to describe, the project to understand neutrinos better won the Nobel Prize in 2015. It's the 2015 prize, isn't it, David? Just though to return to the special nature of David, he won the 2006, is it, or 8? I can't read my text. 6 Rutherford Medal of the Institute of Physics, and of course it was for his contributions, great contributions to the field of neutrino physics. In relation to the work that led up to the Nobel Prize, he has been the spokesman for one of the great teams that led to the discovery he's going to tell us about. So, the real show, David.
I'm not quite sure what a special supernumerary fellow is either. I think the rough translation into English is, well, we don't actually need this fellow, but I suppose we'll have him anyway. I do know there are only 2 special supernumerary fellows at Balliol, myself and Andras Schiff. And any time you're in a category of 2 with Andras Schiff, you're doing well. Sadly, he's rather better at the piano than I am at the guitar. Right. So today I want to tell you a bit about neutrinos and neutrino physics and the discoveries that have led to our being awarded the Nobel Prize in Physics last year, or rather Art McDonald and Takeaki Kajita, 2 of my colleagues. I actually work on an experiment with both of them, 2 different experiments. And also probably it attracted less attention, but the Breakthrough Prize in Physics last year was also awarded to us for these discoveries. But what I really would like to talk about today, a bit more than just my normal neutrino talk, is to emphasize the impact that Balliol has had on these experiments, which is not small, as I will say. Okay, so what are neutrinos? If you give a talk on gender and authority, most people think they know what gender and authority is. Very few people claim to know what a neutrino is. So I have to start off explaining what are neutrinos. Well, I'm a particle physicist, which means I'm a person who tries to study the most fundamental constituents of nature. Of course, we don't even know what the most fundamental constituents of nature are. So we study the most fundamental constituents of nature we can find at any given time. And we try to elucidate the rules by which they interact, hoping that that knowledge will then underlie our knowledge of all the physics at higher scales above it. And as you've probably heard in the news, we've been rather successful at that recently. We have something we call the Standard Model of particle physics, and it makes quite a number of predictions, and it's annoyingly successful. It is made up at the most fundamental level of a set of particles. We call these fermions, for reasons I won't go into, because it's supposed to be a shortish talk. These are the building blocks of nature. So, for instance, we have quarks. This is an up quark and a down quark. If you take 2 up quarks and put a down quark with it and put it in its lowest energy state, you have a proton. So that's one you heard of back in the day. If you take 2 downs and an up, put it together, you get a neutron. Put a neutron together with a proton, you make a deuteron, which is the nucleus of heavy hydrogen. We'll come back to heavy hydrogen again and again because it's rather important to the story. And then you can put that together and make heavier nuclei. And then if you take electrons and let those go around the nuclei, you make atoms. You put atoms together, you make molecules, and then it's off and it becomes chemistry and biology and all that other stuff, and the particle physicists lose interest. We like to stick with the simplest stuff. Now, the first thing you notice is in this what we call a family, there are these particles I've just told you about. And then there's one more called the neutrino. It wasn't at all clear why that was needed at first. In fact, when it was first proposed to exist to explain some anomalies that were seen in early measurements of radioactivity, whereby energy and momentum seemed to just disappear, at first it wasn't even understood if that was a problem. No less a personage than Niels Bohr suggested, well, maybe energy and momentum aren't conserved in individual decays. They're conserved overall, but like entropy. Entropy is a statistical quantity, and you can make strong predictions about the entropy of a system, but you can't make any statement about the entropy of a single particle and make any, you wouldn't expect that to be conserved. My advisor's advisor, a guy by the name of Wolfgang Pauli, was horrified by this prospect because he was trying to construct what we would now call field theory. At the time, nobody paid much attention. And he knew that if he wasn't quite sure what he needed at that point, but he knew one thing for sure, he needed energy to be conserved. So he hypothesized that maybe this missing energy and missing momentum was being carried away by little neutral particles, which he actually called neutrons. Then that was in 31 and 32, Chadwick at that other place where it's kind of wet, discovered the thing we now call the neutron. So somebody asked Fermi, is that Pauli's neutron? And Fermi said, no, it's too big, too heavy. Need a little bitty one, neutrino. So neutrinos they are. So what is a neutrino? Well, a neutrino is very similar to this, the electron. If you take away the electron's electric charge, and you take away almost all of its mass, what you have left is basically a neutrino. By the way, I can sum up the rest of the talk in my entire scientific career, the word almost. When I started, you would have said you took away all its mass, you had a neutrino. But in true Douglas Adams form, I've spent my career changing that from all of its mass to almost all of its mass. Some people say there's no progress. Okay, so this is these particles make up pretty much everything in the world you see around you, right? And one of the first mysteries of the Standard Model, now a few more words about neutrinos. As I say, they're sort of the black sheep of the building blocks of matter because you don't actually need them. They don't build anything. You don't build anything out of neutrinos. They're emitted in certain types of radioactive decay. But, you need electrons, ups and down quarks to make the matter in this building, but you don't need neutrinos. Now, here's the first weirdness, and this was discovered in cosmic ray experiments fairly early on, which is there's actually two almost identical copies of this family. So in addition to the up and the down quark, you got the charm and the strange and the top and the bottom quark. And the electron has two heavier cousins, the mu and the tau. And to go with them, you have the nu mu's and the nu tau. So there's actually three of these families. Why are there three? We don't have a clue. Why aren't there four? We don't know. Why do you need more than one? Who knows? So this is one mystery. This is called the flavor puzzle. For reasons best known to the people who first did it, these are called different flavors. So up, charm, and top, these are the three different flavors. And why there are three flavors, we don't know. But there are three different neutrinos, and that will become very important to this story. Now, neutrinos interact only weakly with normal matter. Now, I mean that both in the technical and in the vernacular. In the technical sense, okay, what do we mean by interactions? Well, in addition to these fermions, there are also these things which we call bosons, gauge bosons, and they are particles which carry the forces. Okay, so these particles interact by exchanging these, right? These are the manifestations of the fields that make up the underlying forces of nature. So this is the photon, which is this laser pen is emitting, the thing that carries electromagnetism. That's the gluon that carries the strong force that binds the quarks together to make protons and neutrons and binds the protons and neutrons together to make nuclei. And then you've got not one, but two. What would you pay? You get two kinds of the weak interaction carried by these two separate particles, the W particle, which will actually change an electron into an electron neutrino, and the Z, which carries something called the weak neutral force. The Z is not electrically charged, and so it doesn't change the electric charge of something. It interacts with all of these things, but it only does so weakly. So why do they call it the weak interaction? Well, because it's weak. Sometimes our jargon is remarkably descriptive. So what do I mean by weak? Well, I'm about to tell you about the neutrinos emitted from the sun that Denis alluded to a moment ago, zillions and zillions of them coming through this room every second. Let's say that, I don't know, Donald Trump convinced me that the immigration of these neutrinos was a problem and we had to stop it. And we were going to build a wall, right? And we'd get Mexicans to pay for it, so it didn't matter how much it cost, right? How big a wall would I have to build to block out those neutrinos? Well, the answer is uncomfortable, even for a man as resistant to fact as Donald Trump. If I wanted to formulate a more modest goal of simply stopping half the neutrinos coming from the sun, I would need a wall of lead 9 light years thick, or a little thicker, a little more than twice the distance to the nearest star. So that is what we mean by weak. It has some advantages and some disadvantages. The advantage is, because the interaction is so weak, we believe we should understand it exactly. We should believe we should be able to make exact predictions of the properties of things under the weak interaction. So if you see any deviation whatsoever from what you predict, it's interesting. The drawback is the 9 light years of lead. It means that you build a great big detector and the neutrinos that hit it just go straight through. Almost every single one of them. And so you need great big detectors, huge fluxes of neutrinos, low background, and a lot of patience. And funding agencies who, for some reason, fund us, even though we're clearly barmy. So the neutrinos interact only weakly with matter. When I started, this picture that is used by all particle physicists came from Fermilab, and they left out one, the Higgs boson is the only other particle in the standard model. They probably left it out because they knew they wouldn't discover it. But as you probably heard, it was recently discovered at CERN, and Nobel Prizes were handed out all around. I should point out, by the way, one of the reasons why particle physicists are so impressed by the standard model of particle physics is that particle carries an entire new force of nature, and this particle is a fundamentally very odd thing. It's a scalar field with a non-zero vacuum expectation value, meaning it's a particle that exists in the vacuum all the time. Both of those were predictions of the mathematics of the model. No one had ever seen a weak neutral current, the interaction of a weak neutral particle due to this. No one had ever seen such a thing when the mathematics of the standard model were written down. But when Peter Higgs wrote down, and many others wrote down the mathematics, those mathematics required the existence of this, and furthermore predicted their properties with great precision. And we have now observed them both, and their properties conform pretty much exactly to those predictions. Well, in fact, exactly to those predictions, to the accuracy with which we can measure. So that tells us it wasn't a lucky guess. That tells you the standard model probably is a description of nature at a deeper level, which I'll come back to. So when I were a lad, when I started in this game in the late 1970s, neutrinos in the standard model were described, of course, when I started in this game, there were only 2 families because the tau had not yet been discovered, and so it wasn't known this 3rd family existed. Neutrinos were thought to be absolutely massless, as I said. There was a lepton flavor number, so it was strictly conserved, which is a fancy way of saying if you have an electron neutrino, it never becomes a muon neutrino. And if an electron neutrino interacts with something, it always makes an electron. It never makes a muon. Okay? And they're always left-handed. Okay, that's weird. But that's the way it is. It was and still is. Well, actually, that's not true. That now they only interact left-handedly. They're not always left-handed. I won't go into that, although that's a really weird thing. And it's another thing we're trying to explain. But let's get back to our neutrinos. Okay, so these properties were held to be true of neutrinos when I started in this game, and there was no reason to believe they weren't. And so where do we go from here? Well, the story begins with a couple of guys, a couple of amazing scientists, who actually were not trying to measure the properties of neutrinos at all. They were trying to use neutrinos to probe the fusion reactions in the core of the sun. Our sun is an absolutely prodigious source of neutrinos, specifically, if you believe the standard model of particle physics, in electron neutrinos. And those neutrinos arise from the nuclear reactions that power the sun. Our sun works by thermonuclear fusion. You have 4 protons. 2 of those protons collide, undergo a weak interaction, emitting a neutrino, and changing into a deuteron. So that's a bound state of a proton and a neutron. It is heavy hydrogen. It has an electric charge of 1, so it has the same chemical properties as hydrogen, but its nuclear properties are very different. And of course, if you take 2 of those heavy hydrogens and combine them with an oxygen molecule, you make heavy water. You've probably heard of heavy water. Yes, this is actually heavy water. If you come up here afterwards, you can see that the emblem on this is a Viking boat. And that's because this particular heavy water came from a plant in Norway, a place called Vermuk in Norway, where they make heavy water. We'll come back to that in a bit. Now you've got 2 deuterons, so that happens twice. You've got 2 deuterons. The deuterons collide with another proton, make helium-3. In the process of this interaction, by the way, they emit a positron, the antiparticle equivalent of an electron. That annihilates with an electron it just finds in the core of the sun and turns into gamma rays. And then those thermalize in the core of the sun and just become energy that heats up the core of the sun. And so you make 2 helium-3s. Eventually the helium-3s collide and make beryllium-6, which then sheds 2 of the protons. And the net effect is that 4 protons turn into a helium-4. So 4 hydrogen atoms turn into a helium-4 atom. You emit energy in the form of these gamma rays and 2 neutrinos. Okay? Now, why did anybody care? This was a hypothesis, although Hans Bethe had already got the Nobel Prize for figuring this out, or actually figuring out a more complicated version of this. There was interest in observing this directly because actually there is no signal on the surface of the sun that this is actually happening. Okay, so these photons, these gamma rays, eventually scatter down and become thermal photons. And, you won't be surprised to discover the sun is not transparent. If you hold a newspaper up on the far side of the sun, you can't read it, not just because it's a long way away. The photons actually have to random walk out of the sun, and that takes a time of order 10,000 years. Okay? But actually that time isn't interesting because the photons, by the time they wander out, they've been thermalized, so they lose all the information about where they come from. They're just from some hot bath. And so the only information they carry out is what's the temperature of the thing I came from. And so to change that temperature, so to make any difference in the flux, you have to get rid of some of the gravitational binding energy of the sun. And that's another time. It's called a Kelvin-Helmholtz time. It's 10 million years. So, roughly. So if you look at the sun today, you won't see it because it's behind a cloud. But if you pick another day and look at the sun, the photons you see are average the nuclear reactions over the last 10 million years. Okay? And so let's say something were happening in the core of the sun fast compared to 10 million years. Let's say in some crazy way the nuclear reactions were going up and down by a factor of 2 every 10 years. Right? There would be no signature of that on the surface of the sun. It would look just the same. On the other hand, the neutrinos, remember the 9 light years of lead, the neutrinos come straight out at the speed of light. At almost the speed of light. So if you could look at the neutrinos, you could see the interaction, the nuclear fusion taking place in the core of the sun directly. Okay, so can you actually do that? Well, 2 quite amazing guys. I have a version of this talk where all I do is talk about Ranjan, but this is supposed to be about Balliol. So Ray Davis and John Bacall. Ray Davis is your true experimenter. He's the kind of guy who could make, who could hack a piece, a quite high quality piece of apparatus out of a banana skin in an old hangar. And John was a theorist who unique amongst astrophysical theorists of his era, used to get the right answer. John and Ray combined to convince the vice president of research at Brookhaven National Laboratory, and Ray is one of the nicest guys, Ray and John both are two of the nicest guys I ever met in science. Incredibly competent, but so friendly, so self-effacing. And the only time I ever wanted to punch him is when Ray told me that the only funding application he ever put in for his Nobel Prize winning experiment, so he had another Nobel Prize winning experiment, not the ones I'm going to talk about later, was when he and John went to the vice president of research at Brookhaven and explained the experiment and said, can we have the money to do it? The guy thought for a minute and said, well, yeah, okay. That was it. That was the only funding application he ever put in. Those of us these days who spend our times filling out Encyclopedia Britannica thick sheafs of forms to collect $100 million, so okay. But anyway, so Ray and John decided they wanted to do the experiment. Now, the 9 light years of lead, are they just crazy? Is this possible? Well, the thing that makes it possible is this huge number of neutrinos. So let's do a quick calculation. We're now going to do actual calculations, so get your mathematics ready. So the net reaction, I told you before, is 4 protons turn to helium-4, 2 positrons, and 2 neutrinos. We can measure the masses of all these things in the laboratory quite accurately. And when we do, we discover that each time you do that, it releases 4 times 10 to the minus 12 joules, or in the units that we like to use in particle physics, 25 MeV over C squared per helium nucleus produced, or since there's 2 neutrinos, half that per neutrino. Now the solar constant is 1.3 kilowatts per meter squared at the Earth's orbit. So if you go outside, well, not here, but if you live on the equator and you wait at noon and you stand outside and you look up, there's 1.3 kilowatts going through each meter squared. Not quite because of the Earth's atmosphere, but anyway. That is the amount of energy going by. So now if we do the uniform spherical cow approximation calculation, we forget everything else. We forget rotation of the solar core or anything. You can just divide that number by that number and calculate how many neutrinos would have to be going by to explain that amount of energy. And when you do that, you get 6.65 times 10 to the 10 per centimeter squared per second, or 67 billion per centimeter squared per second. So if you now look in the direction of the sun, which should be about there, if you look in the direction of the sun, you've got 67 billion neutrinos passing through the pupil of each eye every second, right? Of course, they're neutrinos, so you can look this way. They'll come right through the back of your head. You can wait till midnight, look down, come up through the ground, don't care, okay? So it's this enormous number, 67 billion per centimeter squared per second, gives you any chance to detect them. The good news is this is accurate to better than 10%, believe it or not. In fact, if you allow me a generous definition of what's a solar neutrino, that's actually accurate to a few percent. Bad news is we left out a few things. We'll come back to that. Okay, so you got this enormous number, and then John calculated that with a detector that was big enough, and I'll come back to the detector itself in just a moment, you ought to be able to detect them. But there's a problem. Many problems, actually. But the first problem is straightforward. The Earth's atmosphere is constantly bombarded by cosmic rays coming from something out in the universe. That's a whole set of lectures of its own. So you have these big high-energy particles coming in from outer space, colliding with the upper atmosphere and producing a shower of particles. And on the way down, you make lots of pions. And the pions decay, and the pions decay to make muons and muon neutrinos. Okay? Well, the muons, these heavier cousins of the electron, actually for reasons I won't go into, are very penetrating. They will go through a lot of material. So these highly penetrating muons come down here and hit us at sea level. In fact, there's roughly 1 muon passing through every 100 square centimeters, about that much. So there's 1 muon from cosmic ray interactions going through there every second. Okay? So what's the problem? Well, they make a background. Any muon which hits your detector is quite likely to produce a signal of some sort. And if there's 1 for every 100 square centimeters per second, the solar neutrino rate, we know that huge flux, but then you have to multiply that times what's called the cross-section, the probability a neutrino will interact. That's a very, 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 very tiny number. That's why the 9 light years of lead. But it's not 0. So you multiply that huge flux times the cross-section, you should get an interaction, something like 1 interaction from a solar neutrino in every 100 tons of detector per day. So if you compare that number to that number, you get that there's roughly 1 billion times more events from those cosmic ray muons than there are from neutrinos, right? So how do you get ever going to see the neutrinos in all that muon background? Luckily, Ray and John had this problem in the mid-60s. In the mid-60s, the United States had a large cadre of loyal and energetic scientists who were willing to look into such problems. And so Ray and John asked one of them to help them out, and how would they ever see these neutrinos in the muon background? And here was his response.
It would be quite easy. At the bottom of some of our deeper mine shafts, radioactivity would never penetrate a mine some thousands of feet deep.
Bingo. Dr. Strangelove gets it in one. We really have never come up with anything cleverer than just pile rock in the way, right? To block the muons, you ought to do something intensely clever, and I ought to sit here and tell you about some amazing thing. And the only amazing thing we've ever thought of is go 2 kilometers underground and use 2 kilometers of rock to get in the way. And that's what we do. So Ray built his detector, which consisted of 650,000 liters of perchloroethylene, which is a fancy name for washing up liquid. It's in a huge tank car, and this is 4,850 feet underground in a mine in Lead, South Dakota. And there it is. And in that perchloroethylene, solar neutrinos interacting with the chlorine atoms in the perchloroethylene will change the chlorine 37 in the perchloroethylene into argon 37. And so if you wait for a while, argon 37 starts to build up inside the detector. And then you sweep helium through the detector, and it sweeps out the argon 37, which is radioactive. And so you count the decays of that argon 37 back to chlorine 37, and by counting the number of those atoms, you can measure the solar neutrino flux. This is the complete data set from the experiment for its entire lifetime. For those who can't read, it's a bit small. This goes from 1970 to 1995, so 25 years along here. Each of these dots corresponds to sweeping the detector with helium and counting how much argon you get. And if you look over here, this is the rate, argon 37 production rate in atoms per day, and you can see the average is about a half. Right? So on average, every other day, 1 atom of argon is produced in that enormous tank car. So the first reaction when Ray did this measurement was, yeah, pull the other one. Ray did, however, manage to convince all of us over the years that he could actually do this experiment. And averaged over a very long period of time, 25 years, that was his answer right there. Okay, it's 2.5 SNU, where a SNU is a solar neutrino unit. The problem is, John McCall had done the calculation, and that's up here. And that difference is called the solar neutrino problem when I started. Right? Why does Ray see 1/3 as many neutrinos as John predicts? Well, of course, at first people just assumed that Ray had screwed up. So another experiment was done in a place in Japan called Kamioka. I was there 2 weeks ago. Kamioka is a place. This experiment is called Kamiokande. It's Kamioka NDE, nucleon decay experiment. It was trying to see if the protons in water are stable or if maybe they decay. It was looking for something called proton decay. And so it's a big tank of water surrounded by photomultiplier tubes, which are very sensitive light detectors. And they look for a little flash of light that would be emitted when the protons decayed. But once you have this, it occurred to Kashiba-san, who run it, and an Al Mann, a friend of mine from the University of Pennsylvania, that you might also be able to see neutrinos from the sun by their billiard ball scattering off the electrons. So the neutrinos from the sun would come down, they would scatter off the electron. The electron would be traveling faster than the local speed of light. Now, you all know you can't go faster than the speed of light in a vacuum. Einstein won't let you. But in a transparent medium like water, light actually slows down. And there's no rule that says you can't travel faster than that speed of light. And if you do, a charged particle traveling faster than that speed of light will emit the optical equivalent of a sonic boom. It's called Cherenkov radiation. It's just blue light. Have any of you ever seen Cherenkov radiation? Yeah, you have. You just don't know it. That is a swimming pool nuclear reactor. This happens to be the one at the Institute for Lou Langevin in Grenoble, where I have another experiment. But that blue glow that you see is actually Cherenkov radiation. All the radioactivity emitted by the core of the reactor down there is scattering electrons in the water. There's a pool of water here that's cooling the reactor, and that emits this blue glow. So using these phototubes, now that is an enormous amount of light that you can detect it with your eye or a camera. Using these sensitive photomultiplier tubes, we can actually see the Cherenkov light emitted from a single particle. And when that was done, what was seen was, okay, now of course there's lots of ways to get electrons in a big tank of water from radioactive decays, and so there's lots and lots of these events. However, the ones that have to do with the sun should point straight away from the sun. And so if you plot the angle of an event that you see versus the sun, okay, these are events traveling back towards the sun, these are events traveling straight away from the sun, and you plot them, the dots are the data. You see this peak, see that point up there? See this peak pointing straight away from the sun. So that's proof that we've detected neutrinos, because this was done 1,000 meters under the ground. So how did it know where the sun was if it wasn't neutrinos? Nothing else will go through 1,000 meters of rock. And so that's proof of the detection of solar neutrinos. But the expectation is this line up here, and what was seen was this here. So once again, the rate is much smaller than expected. So that proves it wasn't just John screwing up, or Ray screwing up. So maybe it was John screwing up. For reasons I won't go into, people doubted this precision of this prediction, because it was based on seeing a very small high-energy side branch of the solar neutrino flux. And so if you really wanted to convince people, you had to see those neutrinos I showed you before, the PP neutrinos. And in order to see them, you had to do a new experiment. The new experiment was done in a place called Baksan in the Soviet Union. I participated in this. This is a cavity that's 4 kilometers underneath Mount Anderchi in the Caucasus, where we did a very similar thing, except we had 60 tons of liquid metallic gallium. And in the gallium, you'd get occasionally an atom would change to germanium, radioactive germanium. And we would count it in one of these detectors, which I built at the Los Alamos National Laboratory. Guess we need the light now. If you want to ask me about them later, the thing about neutrino physics is everything is more work than it looks like. That doesn't look so complicated. It looks like some glass and a piece of metal and a few wires. Actually, nothing is what I just said it was. It's not glass. It's supersilk quartz, which is quartz made out of the same zone-refined silicon that you make computer chips out of. That metal is zone-refined iron, 6-9s pure. The wires are tungsten, and those are the only 3 substances used in the manufacture of this. So all the seals have to be made by welding, which is responsible for me wearing these things these days. But anyway, we did it, and the advantage of this is you can see the lower energy neutrinos, and when we did it, lo and behold, what we discovered was that, once again, the standard solar model prediction was a factor of 2 too high. So what in the heck is going on around here? Everybody who looks for solar neutrinos doesn't see enough. Okay? It doesn't look like it could be an astrophysical explanation. I mean, there is no way that you could suppress the flux by a factor of 3 and still conserve energy in the sun. There just doesn't seem to be any way to do it. So could it be particle physics instead of astrophysics? And here I have my handy demonstrate what it could be apparatus. Neutrinos, as I said, the 9 light years of lead, a little hard to discover, a little hard to observe. So we've had some neutrinos made of brass. Okay? What is a neutrino? A neutrino is a particle. What is a particle? A particle is, in the modern jargon of particle physics, is an excitation of a field. Okay? Just like you have electric fields, right? You have different types of fields, electron fields, muon field. And an excitation of that field is a particle. And the mathematics of it means that an excitation could be represented by an oscillator. So here are oscillators, pendula. So let's call that an electron neutrino field, and that's now an electron neutrino. So I've created an electron neutrino. This electron neutrino will now propagate out to the edge of the observable universe and never do anything whatsoever of any interest in the standard model. Okay? Now let's say this is the muon neutrino field. I can make muon neutrinos as well, and they will do the same thing. Okay? However, let's say the standard model is wrong. Let's say there's physics beyond the standard model. And in particular, let's say that neutrinos have mass and that this lepton flavor quantum number is wrong. In reality, they can mix. Okay, now, if you work at CERN, you've got a budget of $1 billion a year, right? So you can afford to have really expensive new physics. We neutrino physicists have to get by with much smaller budgets. So here's our new physics. Okay, I brought it from Staples. Can have a whole bag of new physics for £1, right? And the effect of that is to couple the fields. Okay? Now if I couple the fields, now watch what happens when I make an electron neutrino. Now the energy starts to leak into the muon neutrino field. In fact, I can get it all to leak into the muon neutrino field. And then if I wait a little while, it leaks back. Right? And if I wait a little while longer, it'll leak back into the muon neutrino field. And so what does that correspond to when you make a measurement? Well, when that stops moving, that means my electron neutrino field isn't excited anymore. So my electron neutrinos have gone away. Where'd they go? They became muon neutrinos. And then they cease being muon neutrinos. They become electron neutrinos again. And that's why we call this neutrino oscillations. They switch back and forth and back and forth and back and forth. So why? Okay, fine. If you believe in rubber bands. Why is that interesting? Well, the experiments I've told you about up to now can't see muon neutrinos. They only see electron neutrinos. So if this were happening, then that would explain why they see lower rates. Okay? If this were happening, by the way, then the standard model is broken. Because 2 of the things I told you about neutrinos are wrong. Right? I said they were massless. They have to have mass for this to work. And I said that there was a conserved lepton flavor number. And that can't be true either because an electron neutrino became a muon neutrino and, didn't produce anything else in the process. Okay? So that got people interested, excited, in the way that scientists get excited about strange and obtuse things. And so then it was time to do an experiment to check it. So what do? Well, it's particle physics. So you go get 400 of your closest friends, and you go annoy ministers in several countries, in this particular case in Canada, the United States, and Great Britain, until they give you $100 million to get out of their offices and leave them alone. And then you run off and you build this. This is an artist's rendition of the Sudbury Neutrino Observatory. It consists of an acrylic sphere, okay, which is 12 meters in diameter, 2 inches thick, in which contains 1,000 tons of heavy water. As I told you, this is how, now you can see it a little well, this is heavy water. Now, I'm not going to explain this, but if anybody wants to ask a question later on, because it's not really directly relevant to the talk, I said this is heavy water from that plant in Norway, Vermouth plant. Believe it or not, this little bottle is also heavy water from that same plant in Norway. But this has a slightly different history. This was purchased in the 1970s for use in making accelerator beams at the Rutherford lab. This heavy water was stolen by the Germans and was being returned from Norway back to Germany at the end of the Second World War and was actually sunk in Lake Tinn by the Norwegian resistance to prevent it falling into the hands of the German bomb program. And we went and we got it back out of the bottom of Lake Tyn, and it's for a television program. I'll tell you about it if you want to hear about it. But anyway, so you have 1,000 tons of heavy water. It's available only in Canada in those quantities. That's why we did this in Canada. It's worth $300 million. So, and it's not ours. So we have to make sure we don't lose it. That is surrounded by a polygonal stainless steel structure with the same morphology as a soccer ball, on which are mounted 10,000 of these very sensitive light detectors called the phototubes. Okay, 10,000 8-inch photomultiplier tubes, each one about that big, each one capable of detecting a single photon. And that's all suspended inside 6,500 tons of light water, ordinary, well, it's not ordinary water at all. It's cleanest water in the world, but, and the whole thing is 2 kilometers underground in a nickel mine in lovely Creighton, Ontario. And here's somebody trying to find the on switch for scale. Now, this costs $100 million. Why would you do a damn fool thing like that? You're trying to take advantage of the fact that the deuteron is the most weakly bound of all nuclei. So actually, neutrinos interacting with deuterons in the heavy water produce 3 interactions which you could see. The first, this is elastic scattering. That's the one that Kamiokande and its huge cousin Super K, I'll come back to, has already seen. So we forget that one for now. There's 2 more. There's the charge current reaction, which are those W's. Remember I said there were two weak interactions, charge currents and neutral currents? The charge current, an electron neutrino hits a deuteron, makes 2 protons and an electron. That electron carries information about the direction to the sun, and it also emits Cherenkov radiation, so we can see it with all those phototubes. That enables you to measure the instantaneous electron neutrino rate. Well, great, but we already done that, so that's not worth $100 million. The $100 million is in this. Any neutrino hitting a deuteron can just bust it up into the neutron, the proton, and the neutrino keeps going. If you can count those neutrons, you can work out the total neutrino flux, right? Because this is a neutral current interaction, and the probability of this happening doesn't depend on whether the neutrino is a nu mu, a nu e, or a nu tau. So it measures the total neutrino flux. So if these neutrino oscillations are happening, then this flux should be a factor of 3 lower, based on previous experiments. But that one should be exactly what John Bacall predicted. So that's the signature for this thing happening. And what it requires us to do is to count these neutrons. Okay, so that's why we built it. So why did it take? It actually took a long time, over 20 years. And in fact, it took about 5 years longer than it was supposed to. And so the reason is the enemy. And what is the enemy? The enemy is uranium and thorium. People think uranium and thorium are weird exotic stuff that only found in the Belgian Congo and makes ants get 50 meters long and all this. And total rubbish. Uranium and thorium are absolute ubiquitous contaminants in all crustal rock. That stone right there is about 1 part per million by mass uranium and thorium. I say that with great confidence because all stone is to within a factor of 3 or 4 up or down about 1 part per million uranium and thorium. One thing I like to tell the students is I say, well, you got a nuclear reactor, right? A nuclear reactor is this evil, awful, dangerous thing. We all know it'll leap out and strangle you in your sleep, right? And in it is uranium and thorium, right? No thorium in our current reactors, but there could be. It's full of uranium. And that reactor sits in a containment vessel, which is a big concrete thing 2 meters thick and quite large. And that sits inside a turbine hall because the hot water drives turbines, and that's a big concrete building, right? And that sits next to an office building, big concrete building where all the workers work. And in front of that's a big concrete parking lot where they park all their cars. And you take all that concrete, add it up, multiply times 10 to the minus 6, you find out there's more uranium outside the core of a nuclear reactor than there is inside the core of a nuclear reactor. Now, most people don't worry about all that other uranium, but we have to. Because the uranium and thorium, it's radioactive, and in the decay schemes, I won't go through the details of all these decay schemes, but the uranium decays through many alpha and beta decays till eventually it reaches lead isotopes, which are stable. And in the process, it makes betas and gammas that can produce light. And that light interferes with our ability to see signals at low energies. And worse, some of these gammas, in the cases bismuth-214 and thallium-208, decay and produce gamma rays with an energy above 2.2 MeV. And those gamma rays can hit a deuteron and break it into a neutron and a proton. And when that happens, you've got a neutron. And that looks just like a neutron that came from solar neutrinos. And so, in order to do this experiment, we have to get rid of all the uranium and thorium so this doesn't happen. And that actually isn't the hard part. The hard part is you have to prove you got rid of all the uranium and thorium. There's no good getting rid of it if you can't prove you got rid of it. And so the design for the detector called for spectacularly low levels of uranium and thorium in everything. The highest precision required for the D2O itself, 10 to the minus 15 grams per gram. That corresponds to an amount of mine dust that you could pile on your little finger in our 1,000 tons of heavy water. If you've ever been in a mine, an amount of mine dust that you can pile on your little finger can be found on your little finger at all times, right? And so getting rid of all that was a bit of an issue. I would love to go through the construction of this because I spent a fair fraction of my life doing it. First thing you need, that's the phototube support structure assembled for testing at the university, at the Lawrence Livermore National Laboratory in California. That's a hole in the ground. This is the cavity. You can't really see it in this light, but there's a big earth-moving piece of equipment here. And if you come over here and look carefully, you can see these guys are standing in ankle-deep muck. That is that hole in the ground converted into the world's largest Class 10,000 clean room in a mine, 2 kilometers underground. Did I point that out? I think I did. And the top half of the phototube support structure constructed within it. Here is the acrylic vessel beginning to be assembled. See, the problem is every single thing that goes underground has to go in what's called a cage, which is what miners call elevators. Or, I'm sorry, what Americans call lifts elevators. Miners call elevators cages, okay? The cage had a door that's just about the size of that one right there. So you have to picture every single thing in this cavity coming through those doors. You need your 12 meter in diameter acrylic bubble to come through those doors. Needless to say, it won't. So you cut it into sections, and then you have to glue it together underground. Except A, you can't use glue because it's too radioactive, and B, you can't get any dust in it while you're doing it, right? So it was a pain. And here it is. Now the acrylic vessel these are sheets inside to keep the inside clean. And the phototubes are beginning to be mounted. And here's a shot as the last bit of the acrylic vessel is about to be put on. You can see it going up here. These specially thickened grooves around the waist hold the ropes that will hold it up. Remember, heavy water is 10% denser than light water. So that means 1,000 tons of heavy water still weighs 100 tons even when suspended in light water. And you don't see a lot of acrylic bridges out there. You know, acrylic is not your ideal engineering material. So it was a challenge to do this, and we had to convince AECL, who owned the $300 million worth of heavy water, that it wouldn't break and we wouldn't lose it. And then they didn't believe us. So then they got Lloyd's of London to insure it, and then we had to convince Lloyd's of London. And luckily we did succeed in convincing them up until 9/11, when 9/11 had no impact, as far as I can tell, on the stability of acrylic structures, but it did make insurance companies really, really, really scared about losing lots of money. And so their rates went boom, and our experiment went, but luckily by that time we'd finished it. Right, and then eventually that was finished. And then we put in all those phototubes. These things, by the way, these things that look like bicycle reflectors on your bicycle headlight, they almost have that function, although backwards. They focus the light down onto these phototubes. Those were actually all made in Oxford, and there's a huge story about that because ultra-pure water is almost an ideal acid and ideal base. Put any normal mirror in it, and you've got a sheet of glass inside about an hour, right? So these were all made of a special birefringent material. They were interference mirrors where you have layers of different index of refraction. And they're, oh God, I can't even remember now, calcium fluoride, praseodymium oxide, and another one. And it was really hard to do, and the company that made them went bankrupt. Oh well, impact. Eventually we were done, phototubes all around, acrylic vessel inside, fill it full of water. Sure enough, there's your solar neutrino. Now this really doesn't show in this light. Each of these dots is a phototube that was hit by a photon, and you see this little ragged ring, which is exactly what you expect to see from a solar neutrino. Okay, so now I would like to spend about a week going through all the calibrations and backgrounds and systematic errors and all that, but you don't want to hear it. Bottom line is this. The charge current signal, which is the one that measures the electron neutrinos, is here. That's how many we saw. That hatched area is what John Bacall predicted we should see. Okay, the elastic scattering, you see here in the green. The neutral current, the one that's the same, the one that it doesn't care what flavor the neutrinos are, and therefore you should get what John predicted. You got bang on exactly what John predicted. So in other words, the sun does emit the number of neutrinos that John said it did. However, by the time they reach the Earth, 2/3 of them have changed from electron neutrinos, which you see with this interaction, into something else, which we now know to be mostly muon neutrinos, but you can't tell that from this experiment. And so, wow, that was amazing. Why am I telling you about it? Okay. The first reason I'm telling you about it is because it's fun. That's why I do most things. The second reason, when I came to Balliol, snow was just about to begin. We had been approved. It wasn't even quite true. We hadn't even fully approved at that point. But we faced many challenges, and here are some of them. 4 of the big ones. How do you build this thing and keep it radioactively clean? How do you clean up all that water and prove you cleaned it up? How do you tell the neutral current from the charge current events? In the end, the neutral currents, these neutrons capture and make gamma rays that make Cherenkov light, just as in that reactor picture I told you, you're making Cherenkov light from gamma rays. How do you tell the neutral current events from the charge current events? And how do you quantify the backgrounds? That's the most important question in snow. Nobody doubted that we could see these events. The hard part is working out that there isn't anything they could come from except solar neutrinos. That was the hard question. Well, the first of these, I had an idea on how to do this when I first came to Balliol, an idea I'd formed when I was at Los Alamos. And so I got one of my undergraduates. I was a tutor here, and I had an undergraduate, a fellow by the name of Steve Bryce. And I talked him into doing a thesis, and he wrote a very good thesis, which was submitted in 1996, on Monte Carlo analysis techniques for the Sudbury Neutrino Observatory. You can see Steve Bryce, Balliol College, Oxford. And here's a plot. This is actually not a plot from his thesis because it's only 20 years ago, but you look back at the thesis and it looks like, it should have been done with a quill pen on vellum. The quality of the graphics was poor back then. Except I can remember at the time, we used to think, gosh, our graphics are so good these days compared to what they were 20 years ago when I did my thesis. Anyway, this is a more modern plot. But it shows we worked out that by looking at I won't go into the details, the exact pattern of the way the phototubes are hit around the detector, you can distinguish neutrons, events due to neutrons, from events due to electrons. So that is a way to tell how many of your events came from neutral current events and how many of your events came from charge current events. There are other ways. This contributed overall to that and made the detector much more sensitive. Okay, that would be good. That by itself made me an FRS. But we had another idea. While we were doing this, it actually occurred, I think it was first to Martin Moorhead, actually, a postdoc working with us, realized that this technique could be applied to an even more important problem, which is how you measure the background. I told you that when you have background events, it made little flashes of light. So clearly you just count the little flashes of light, and that ought to tell you how much background you've got, right? Well, almost. The problem is some of the little flashes of light come from the uranium chain, and some of the little flashes of light come from the thorium chain. And unless you can tell how many come from each, you can't work out how many background neutrons a given number of flashes correspond to. You have to be able to tell the uranium events from the thorium events. And it was suggested that using this technique we might be able to do that. And so we needed somebody to try that. And we came across this fellow, or rather, this fellow asked to come to Oxford to do an advanced degree. His name is Xin Chen. He's a very, very, very bright guy. He was coming from China. This was in the mid-90s. He didn't have any money. Luckily, Balliol had the Dervig-Willis Scholarship. And so he put in for a Dervig-Willis Scholarship. I, of course, in a totally unbiased way, argued his case before the college. And he won the Dervig-Willis Scholarship to get me out of their offices. Neutrino physicists are really good at being annoying enough that people give you what you want. Because, so he got the Dervig-Willis Scholarship, and he attempted to do that in his thesis, and this is actually a plot from his thesis, and was able to show that, yes, you can distinguish thorium from uranium events by these very same isotropy variables, well, not quite exactly the same, but by isotropy variables along the same way. And this was actually one of the absolute key moments in establishing the correctness of the Snow results, because we had two independent ways. There's no way to check this experiment. Nobody else can do it, right? So we have to check ourselves. We had two completely independent ways to measure the background. One, by assaying the water, by taking uranium and thorium out of the water and seeing how much there is. And the second way, which nobody had any idea existed when I moved to Oxford, the second way was this. So here is a slide that outlines those two ways. This is a modern, so flashier graphic version of the plot from Zin's thesis. What we call the in situ measurements, and these are the ex situ measurements. Okay? This slide I took out of a talk. I saw that talk last December in Stockholm. The talk was given by Art McDonald on the occasion of his being awarded the Nobel Prize in Physics for the results of the Snow experiment. And there were only two data plots in his talk, and this was one of them, right? And so that result is from Xin Chen's thesis. And if you don't believe me that it was important, I was in Salt Lake City at the APS meeting. We're celebrating all of this stuff. And Art didn't realize that Xin Chen came on a scholarship. So when I told him that, he asked if he could record a message for Balliol on that topic. And so I apologize for the photography of this. This is done with my mobile phone.
Hi, I'm Art McDonald. I'm the director of the Sudbury Neutrino Observatory, the winner of the Nobel Prize in Physics for 2015. I'd like to personally thank Balliol College for their contributions to the success of our experiment. I would like to comment on the very significant contributions made by Xin Chen, who was directly supported by Balliol, and who made contributions during the data analysis phase of the project that were extremely important in terms of determining a major component experiment, and that is the radioactive background.
So that was Art pointing out that what Xin did, and what wouldn't have happened if we didn't have the Dervig-Willis Scholarship, was to make an important step in establishing the correctness of the experiment. So then everybody believed the experiment and lots of stuff. Snow result made Science's list of the top breakthroughs in science in the world in 2001 and 2002. The only time an experiment has made that list twice, to my knowledge. And of course, it led to last year's Nobel Prize in Physics for Art and for Kajita-san. It's me and Art in Stockholm just after the award. It led to me getting a week of free champagne in the Grand Hotel in Stockholm, so that can't be bad. Who's this guy? Well, I don't have time to go through the details. Meanwhile, the Kamiokande experiment I told you about had a gargantuan offspring called the Super Kamiokande detector. This is really quite large. I've been in it. It's 40 meters in diameter and 40 meters high. Here's three men in a boat. This is the detector. It's filled with these phototubes, which are that big around and that long. I know because I have one in my office. 11,000 of them. This is ultra-pure water. You can tell it's ultra-pure because you can see the phototubes on the bottom of the tank. The tank is half full, so you're looking through 20 meters of water. right? And you can see each phototube on the bottom of the tank. It looks actually, this is another proton decay experiment, but one of the things it looks at are those neutrinos that come from the cosmic ray interactions, the same thing that make the muons that we were worried about and that Dr. Strangelove had to help us with. Those interactions also make neutrinos. And those neutrinos interact within Super Kamiokande. They're very high energy now. We're not talking about nuclear physics energies. We're talking about each one of these has the energy equivalent to the mass of a proton. And the new mu's interact and produce a muon, which goes nice and straight and emits Cherenkov radiation. It makes a nice sharp ring. So each dot is one of those 11,000 phototubes having seen a bit of light. You see this nice sharp ring from a muon. Electrons are light, and they get bounced around as they go forward, and so their rings get all smushed out, and they look fuzzy. So you get these fuzzy rings. So by looking for fuzzy rings, you can count electron neutrinos. For looking at sharp rings, you can count muon neutrinos. And now if you plot your neutrino flux as a function not of the distant direction of the sun now, but of just the zenith angle, right? So this is stuff coming down straight from overhead, and this is stuff coming straight up from below. And then you look at your fuzzy rings and your sharp rings. Your fuzzy rings look fine. The data are the dots. The prediction, I wish they'd pick another color. These vaguely visible blue boxes are the prediction. And the vaguely visible blue boxes and the dots look just fine. For electron neutrinos, all is well. For muon neutrinos, it ain't quite the same, because if you look coming down from above, the vaguely blue boxes and the dots sort of line up. Everything's okay. But coming up from below, the number of events actually observed is half what you expect. Okay? And so this one plot demonstrates that neutrinos have mass. Right? And it demonstrates that because these neutrinos coming up from below know they've traveled further than these neutrinos. And that means they have a clock that is running. If their clock is running, they can't be traveling at the speed of light. The speed of light, all clocks stop. Right? So if they have a clock which is running, they can't be traveling at the speed of light. If they're not traveling at the speed of light, they're not massless. They have to have a mass. So this one plot shows that neutrinos have masses. And an earlier version of this, which doesn't look nearly as pretty because graphics were not as good back then, was in Kajita-san's thesis. And that's why he has Nobel Prize. So what did we do next? Actually, what we did next is hurry up because we've overrun the talk. We took Super Kamiokande. Super Kamiokande sits under a mountain, Mount Ekenoyama, right here near the west coast of Japan. So there's Super K down there on a mountain. We took an accelerator facility here on the east coast of Japan. I wasn't actually a part of Super K then. I am now. And the reason I joined is because of this other experiment. So we took an accelerator facility here on the east coast of Japan at a place called J Park in Tokai. And here's a picture of it. This is a linear accelerator that feeds a ring that's here. And that's the Pacific Ocean, so it really is on the coast. Yes, that is the one, by the way, that had the tsunami. And that tsunami happened while we were doing this experiment. But you can't really make it out, but there's a dune right here. That dune's about 10 meters high, which turned out to be high enough by about 4 meters. So our experiment didn't drown, although the students got shaken up a bit. And the facility got shaken. You should have seen the roads. They look like pretzels. But anyway, we take the protons from this ring and we make neutrinos. And we fire them all the way through the ground underneath Japan and hit this detector. And we have this really complicated, really expensive detector that I helped build here on the East Coast to measure the neutrino beam really well before we send it off across Japan. And when we do that, we discovered that this beam, which should be pure muon neutrinos, because we make it by the decays of those pions, the same thing that are making the muon neutrinos in the upper atmosphere, should be pure muon neutrinos, in fact has electron neutrinos in it. So that's another type of this neutrino oscillation that is interesting for other reasons, and it meant that we all got the breakthrough prize. There's art again, Kajita-san, and this is Koichiro Nishikawa, who's the head of our T-decay, well, that was the head of our T-decay experiment when it started, and various other neutrino physicists I'll tell you about if you're interested. And so supposedly we were told by Mark Zuckerberg that we're now the rock stars of physics. I know all of these people. I've worked with all of them for many, many years, and rock star was not the first word that leaps to mind. So why does everybody care about all this? Neutrino oscillations, the first laboratory physics we have seen beyond the standard model, and it may be far beyond the standard model. We don't know yet. The parameters that describe it are fundamental constants of nature, as far as we know, and that's what we do. We measure fundamental constants of nature. But it turns out the very smallness, the masses you extract from this, by the way, are millions of times smaller than the mass of any other particle. And so the very smallness of those masses may be hinting at the physics of very high energies. That's the source of this question, that they may be far beyond the standard model. We won't know until we make much better measurements. Neutrinos, by the way, are the second most numerous particle in the universe, so even a tiny mass can have cosmological consequences. And these neutrino oscillations may be pointing to the solution of a very profound mystery, which is, where did the matter come from? Why is there any matter in the universe? Right? There shouldn't be. If I take the standard model of particle physics and the standard cosmology that originates in a hot Big Bang, and I extrapolate a hot Big Bang to now, I get a universe that doesn't have any matter in it. Doesn't have very much matter in it. It certainly doesn't have this much matter in it. So that means there must be laws of physics not in the standard model, which are different for neutrinos and antineutrinos. And neutrino oscillations, as I told you, are not in the standard model, are one place that those new laws of physics could be hiding. And so in order to understand that goes by the name of leptogenesis, in order to probe that, we now have to see whether these oscillations that T decay has seen are the same for neutrinos and antineutrinos. And now I'm going to tell you what we need to do that, but I guess, I don't know, is anybody here in the civil service? No? I once did a parliamentary pairing scheme, and I spent a couple of weeks down in Whitehall, or in Palace Westminster, and we were in Whitehall at a reception, and some civil servant says, what are you doing here? And I said, well, I'm doing a parliamentary pairing scheme. I came down to learn how government looks at science, and perhaps to explain to you, why we do what we do and what it means. He looked at me and says, you're a particle physicist, right? I said, yes. He said, we know what it means. I said, oh, indeed. Well, I hadn't realized that the civil service was so well educated in our science, but it's very pleasing for me to know that. By the way, what do you think it means? He said, well, you just made a discovery of some sort, didn't you? I said, well, yes, we just made a discovery of some sort. He said, it's very important, you got prizes and everything, didn't you? Yes. He says, so now you need a bigger one, right? So in order to do this measurement, we're going to build this hypercamiocanda. Hypercamiocanda is 990,000 tons of water, presumably for the same reason that cars cost, $19,995, because nobody wants to pay 20 grand for a car, right? You'd be nuts to build a 1,000,000-ton water Cherenkov detector. So it's 990,000 tons of water with 99,000 photomultipliers. It's roughly 3 times the size of the King's Cross railway station. It will also be under a nearby mountain in Japan, not the one that Kamioka is under, because that's now got a gravity wave detector in it, and I don't think they want us excavating something 3 times the size of King's Cross railway station next to their very sensitive detector. We think this, I just came back from Japan. You can never tell what's going to happen in Japan. I've worked there for 20 years, and I still don't understand, but it appears to be on the verge of approval in Japan, in which case we will spend the next 20 years doing this. Okay, so conclusions. Ambitious experiments. I hope I've convinced you these are ambitious, if nothing else. All over the world. By the way, I've just told you about a small number. There are many others. That's why there are more people on that stage. Have established the new phenomenon of neutrino oscillations, and they broke the standard model. That's what we experimentalists live to do, by the way, is to break the theories. All right? The theorists live to create theories we can't break. These days, often by creating theories we can't test. String theory, they love it, Nah. You can't test my theory. To which we just look at them and say, yeah, but you don't get a Nobel Prize till we prove you're right. Ha! So the initial evidence came from experiments that were looking for something else. Okay, Ray was trying to study the core of the sun Kajita-san was measuring a background of proton decay. Okay? One of the things you always have to remember in fundamental science is you almost never are doing what you think you're doing. You're making a measurement that no one has ever made before. You're making it better than anyone has ever done before. And sometimes you discover stuff that's really boring, right? And sometimes you discover something entirely unexpected, as happened here. We aren't done yet. We're never done. So there are more experiments yet to build, so watch this space. I don't have to retire yet. The support of Balliol donors has contributed directly to this success, as I've laid out for you, so thanks very much. Without the Derviguilla Scholarship, we wouldn't have had Xin Chen. And without Xin Chen, that would have remained a speculation rather than a solid part of the experiment. I'm afraid we need your continued support, especially in the very difficult times to come. British science is about to go through the most difficult time since the war. I'm a director of the Research Council, so that is not just vague concern. It is based on knowing what's going on. It's going to be tough, so we very much hope to have your support. Any questions? And I leave you with this.